So, subsystem responsibilities include distributing commands in hardware form. So these are the electrical signals that are going through wires, through lines between the onboard computer and the different subsystems. The CDH subsystem interacts with every component that outputs data, like sensors and receivers, and receives commands for the actuators and transmitters. So here you'll see a diagram of this processor. This onboard computer has a lot of components, which we'll talk about next lecture, but it does, as a whole, talk to all the other subsystems, like ACS, communications, propulsion if you have it, power, thermal, payload, through a spacecraft data bus. Another subsystem responsibility is receiving data from the receiver, from the communications subsystem, and passing data to the transmitter, which is commanded by the communications subsystem. Other subsystem responsibilities include executing user commands and transitioning between user-dictated modes of operations. This is called event sequencing. And you'll see here a state transition diagram. This is just an example of how you can visualize different modes of operation and how to translate between them. So what you'll see is you would enter this loop at pre-launch initialization. So this is when you get booted out. And then there are conditions to exit this state, such as 30 minutes after, if your clock reads 30 minutes, then initiate checkout, in which you would do a self-test to, let's get a reading from the solar panels. Let's get a reading from the IMU and see if the values fall between this range. So in that self-test mode, you would have conditions to exit that state, say, okay, we're all good. Let's go to a different state, such as, oh, sorry, this is pre-launch. Anyway, once you're in orbit, you go to a different state. You can go to, say, nominal operations. The point is that you have modes with enter conditions and exit conditions that need to be encoded by the flight software. And sometimes these mode transitions happen without user intervention. Without user intervention would be autonomously, to have the code itself do the transition. With user intervention would be a mission operator on ground sending that command to the spacecraft to manually exit, say, one mode and go to another. Another responsibility is to detect, isolate, and recover from spacecraft failures. So here you'll see something like, here's a failure, that's an event. So you want to go into an error contingency mode, in which if you do solve it, then you go back to some nominal operation. Nominal means normal. And if you experience another failure, then you go back to this error contingency. So you see that there are these conditions, failures, that push the spacecraft to exist in a mode that is, we call it safe mode. Safe mode is when the spacecraft tries to turn off as many things as possible, like the payload. It just has the minimal amount of subsystems running and charging so that ground command can figure out what to do next, can figure out what the failure was and then rectify that error. Other subsystem responsibilities include processing the spacecraft data, and that happens in the flight software. Another responsibility is managing or coordinating the passing of data through the software pipeline, for which I have an image of this pipeline here. So we've seen this in another picture, but what's important here is that there's a spacecraft data bus that is this pipeline in which all of the data packets go through, and then the computer can listen in selectively or have all of the messages come through depending on your software architecture. But you can kind of physically intuit that process in this diagram. Another subsystem responsibility is to store and send payload data and spacecraft state of health data. And along those lines, we'd also like to monitor the health and performance of all subsystems. So here you'll see a Cosmos mission operations and support tool where we have a graphic user interface displaying a lot of subsystem data. So in the top left, we have mission events that are coming through time. We have on the bottom left plots of the ADCS data. We have orbit information. We have some graphical visualization of how the spacecraft is pointing in space. We have electrical power system data such as state of charge, maybe some temperature data. We have the communication subsystem gain pattern and potentially some angle from the ground station. So you'll see here that we're not only concerned about the payload data, which is the science mission, we're also concerned with all of the different data that we could collect from the spacecraft to monitor that it's healthy and will operate until maybe we talk to it next or we can anticipate any kind of failures. The lead, very contingent on the subsystem responsibilities, but the lead themselves have to be the owner and primary developer of the spacecraft's software architecture and onboard computer design. So this has two roles. In retrospect, I think I might have separated flight software and command and data handling, avionics, into two different roles. But this part, the software part, you'll see that the Cosmos functional architecture, what you've been working on, trying to launch, has the following capabilities. It has mission planning and scheduling. There are simulators inside of the software. There's the ability to manage data, to operate the payload, to conduct mission analysis and flight dynamics, and then also to resolve anomalies. In the context, the flight software Cosmos is supposed to be able to communicate schedule, task plans, orbit ephemeris, spacecraft uploads to the ground station, and it should also be able to pass ground station status, payload data, and post ground pass reports. How spacecraft engineers interact with Cosmos could be the flight software could communicate mission status. The spacecraft engineers can request tasks to be done to the mission operations team. The mission operations team then interacts with the software by giving those commands to the spacecraft and receiving mission data from the spacecraft. So there is a point to the software that you're working with, even though you don't immediately get to see its capabilities yet. This is the overall larger goal. Other subsystem lead responsibilities include to write software to process, compress, decompress, and manipulate the data. Cosmos itself is a baseline flight software architecture where for your payload, one of the tasks we're going to do later on in the semester is for you to write your own payload script. So we have this software architecture that can wrap around your specific science mission and payload interface. But how do we collect data from your payload? How do we process that data? How much of that data do you want to actually to send through your spacecraft? That's for you to decide. and for us to actually implement later on in the semester. Another subsystem lead responsibility is to manage the data budget and flow of data during operations. So you can do that by writing software scripts. We were just talking about throttling the amount of data that your payload passes through to send to the ground station. So that's one of the jobs. And then also part of the flight software is to encode robustness when failures happen in the form of single event upsets, which are radiation events, and information loss due to compression. Okay, another subsystem lead is to coordinate with the systems engineer and other subsystem specialists and the mission operations team to define the computer system's operational modes and states. Oops, that's redundant. So here we see a mission operations process that was put together by Dr. Sorensen. So we do have the spacecraft that is actually doing the science mission, but there is a ton of coordination, not only in the planning process, but in the flight operations process, between the payload customers, the stakeholders like us, and the spacecraft engineers and mission operation folks. So a lot of these tasks are like mission planning and scheduling, simulating, resolving anomalies, doing spacecraft analysis and orbit trajectory analysis, mission analysis. Yeah, the command and data handling lead and the flight software lead, either separate or together, have to touch a lot of the different subsystems. So that's why communications for this particular subsystem is critical. You should have a hand in a shallow understanding, hopefully deeper understanding of the different subsystems. So I have a question up here that's talking about, there's a lot of talk about software and programming being important, but I assume the lead is something like an electrical engineer. Would information and computer science personnel be brought in as specialists? So yeah, there is the avionics part, which should be handled by the electrical engineer, or is most qualified with an electrical engineering background. In the flight software lead is most qualified if they have a computer science degree. So there's both. I also know that some computer scientists have some computer engineering experience that could help with avionics, and electrical engineers have some experience coding. So there is overlap between these two fields, but it's perhaps best to separate the two. Okay, other subsystem lead responsibilities include communicating with the spacecraft bus components. This could be converting the raw data into sensible information, like converting voltages to, let's say, the amount of flux that you're seeing on the solar panels, determining input and output requirements for the avionics subsystems. There are a lot of different connections between components. We'll talk about that next lecture, but some examples are like USB or UART, I2C. Those different connections have different physical connectors and can also have different message formats. Another responsibility is standardizing the data packet formats across subsystems and across communication channels. So I just mentioned that different connectors like UART, I2C, they have different message packet forms. So when these packets get to the data bus, the data package should be standardized. The CDH subsystem lead also should strategize with the integration and test engineers further along in the process to help develop testing and verification plans for the spacecraft system. Although a lot of the subsystem leads for like EPS and ADCS, they are concerned with verifying their spacecraft performance, the CDH lead is going to be, in the end, handling a lot of that data. So it makes sense that the person handling the data would be the one to verify if the actual physical components perform as they say they should. So here I have pictures of different kind of tests you can conduct. So you'll see in a moment why CDH leads are so involved with the testing process. Because on ground, we have to simulate the space environment. You can do this in two ways. You can predict what the space environment is going to be like in the orbit, and then spoof physical. So you'll take that best guess, that estimate, and then feed it to, say, a GPS transmitter. And then that GPS transmitter would spoof or fake a packet to go to the spacecraft's GPS receiver. Or what you could do is you have a simulation that is totally virtual, and you connect that directly to the spacecraft, bypassing the physical components and just spoofing the GPS position that you would see in your orbit. So there's a lot of software that has to simulate, say, the space environment, the physics. For example, for our rigid body dynamics, you could have a simulator that is totally virtual, that is propagating what the IMU would be reading over time. And then you can also simulate sensor models and actuator models, like the amount of noise that sensors and actuators would measure. And then the device under test. So all of this is testing software. The device under test, you would want to have actual flight software that you want to fly that is being tested. And you also want this device under test to be as similar to the physical configuration that it would be as a fully integrated satellite. So here you see there's this husked out spacecraft with a solar panel that is under test. There are a lot of subsystems that are kind of peripherally supporting this device under test. You see a panel emulator. You see a solar array simulator. That is not how we do it in space, but it is what's simulating signals that you would see in space. Yeah, so this is kind of what a hardware in the loop setup would look like, where you have this hardware, we've got all this test equipment to put it in the loop being some continuous simulation of maybe the progress of mission operations. The distinction here, software in the loop, is that you have a virtual spacecraft, so you don't have any physical components. You're just simulating how different programs in your flight software would react to a simulated space environment. In Cosmos, you are capable of conducting software in the loop tests. There are ADCS simulators for you to enter in your orbit information, your satellite geometry, and then you press play, and you can step through what the software would do in space for your fake spacecraft. It's good to do these kind of tests, like software in the loop and then hardware in the loop, to incrementally test out and debug any kinks in your software, but also in your hardware design. There is a video in the textbook that maybe you've watched where an engineer talks about the significance of doing these software and hardware in the loop tests.